The open channels, I will just talk about this introduction, the study objectives, measurement techniques, and results and conclusion. Now, the open channel flow occurs in natural rivers and streams, canals, and man-made open channel that is partially full flow. The transition, as we can see it, is always rectangular, connected with trapezoidal channels. It's designed to connect these with different sizes and shapes. They are used in treatment plants and in the irrigation system involving rectangular channels. Now, the transition are mainly narrow rectangular channels emerging from reservoir and connected with downstream earth trapezoidal channel. The types of the transition, there's different type. The cylindrical transition is mainly used for small sections and it's easy to construct, but the losses and efficiency is less than the other types. Mainly, we use warp transition and we use wedge transition for larger structures, but this is the cost is little high, and it's always recommended the warp transition because of its efficiency in reducing the head losses and the turbulence. Now, the objective of the study is to examine in the warp transition itself without adding any tools how is the turbulent or how we can do to reduce the turbulence. The project was done at Concordia University in Montreal, Canada. So we use plexiglass to build the flume. It's made of plexiglass sheets. We see this is the warp transition. As seen, it's very smooth, without corner, without edges. It's supposed to be the most effective transition in the open channels. The challenges is the turbulence itself and the eddies. This is the circle that created in the transition. So the problem, it causes the turbulence. It will be propagated, extended to the downstream and cause the erosion of the earth trapezoidal channels, as we can see here. So this is a big problem that the farmer faces in the irrigation system. So in this case, I just want to see that and to check that if this warp transition is the best solutions as it is used as the best transition in the open channel, can we use it just to have a risk with the erosion at the downstream? Now the system consists of head tank, and we have like a contraction section, a rectangular section. Number 4 is the warp transition, and we have trapezoidal cross sections. Now this is the warp transition, and we use acoustic Doppler velocimetry to measure the velocity in the whole sections. I divide it into 12 cross sections. So the flow direction, let's say we can see the right, we are looking to the downstream from the warp transition. So this is a measurements of all flumes and tools we have in the system. Now we have recirculating flumes that we use a big pump with acrylic sheets to reduce the turbulence. And we have a main valve and digital flow meters, and we use gate at the end of the flume to control the water level. Of course, we need to take these measurements to assure that the flow going to the warp transition is laminar and it is uniform. There is no turbulence when it reaches the warp transition. So the measurements, we use this flow meter digital, and we use the acoustic Doppler velocimetry. This is the use the sound to measure the velocity. We move it in a different position. This is the device, ADV. And we use also flow visualization test to just confirm that the results we have experimentally is approved visually. Now, we should, before we start to have configuration of the ADV device, and we use like micro tunnels, microflume to set all these setup data for the ADV. Now, the cross section, we have 12 cross sections, 3 in the rectangular, 3 in the warp transition, and we have 6 on the trapezoidal. You can see the stars showing the position of the probe of the ADV, how we measure it, and all these points, 840 points we have in the whole cross sections. So we need to show the results here and to see one by one how this warp transition work. Now the flow conditions between the flow rate is 20.5, 27.5 liter per second, and we can see the flow was subcritical, and it means low velocities going to the warp transition. The depth we fix it at 300, almost 300 millimeter, and the ADV must be stay in the position for 2 seconds to measure as much as we can velocity in 3 dimensions. Now, the first, we have the results showing the lateral, like the average, the y direction in the left and right, the x is the main flow direction, and the y, the z is the vertical. So we can see the main flow here is very close in cross-section 1 and cross-section 2 in the rectangular before warp transition. As we can see, very close to each other. We call this is boundary layer profile, which is mean that the flow is fully developed and there is no turbulence approaching the warp transition. And we can see this, the vertical velocities that is between mean negative and positive. This is due to the indicate that we have turbulence in the vertical directions. So when we go further in this is 3 and 4, 3 is the last cross section before warp transition, and the 4 is the first cross section in the warp transition. We can see still there is no difference between cross section 1, 2, 3, and 4, but we can see that the vertical is opposite that in cross section 1. It means when the flow is go to positive, it means it is left direction flow, and negative is the right direction flow. When we enter the warp transition, because we have expansion in the flow, so we have reduce in the velocity. So we can see this complicated shape, zigzag from the bottom to the top, and the velocity increase when we go up to the water surface. This complicated profile show that the flow is fully turbulent and it's not stable, and we have possibility of erosion of the earth channels in the downstream of this channel. Now, to understand this is more, we have the contour of longitudinal velocity, the main. This is showing the main velocity. As we can see, the rectangular, the high velocity into to the right side, and the other velocity is fully developed, it's uniform. And we can see this like jet-like course. This is the eddies. This is, we call it eddies. It's a circle that cause the turbulence. And we can see this due to the flow separation. Now, this flow separation force the main flow to go to the right side. And this is accelerated and cause little separation in the corners here. But the main losses was in the, as we can see, cross-section 9 in the left side, and the main flow is going to one side. This one showing from rectangular, trapezoid, warp transition, and the trapezoidal in 9 and 12. Now, to understand this jet, it's like this is 2 dimensions, but this jet give you 3-dimensional view. What I mean, if I look at the plan in the top, we can see this tongue. This is the main flow going to the right side, and the separation is going to the left side. That's showing as the jet here, the core jet and the left side. These turbulence will be expanded to the downstream and will cause erosion and the earth field channels, and of course will reduce the efficiency of the warp transition. So the next one, of course, the erosion is a big problem for the farmers. Now, after that, I conduct dye visualization tests showing that if we put the dye on the left side and the right side, how it will move. So in the first and the left side, it is big. We have big movement. It goes opposite flow direction, reversal flow, because we have expansion in the area, so the velocity will be less. Decreasing the velocity will cause higher in pressure gradient, and that cause the flow separation. The flow separation means the flow is going opposite the main flow. So this has caused the turbulence in the channel. And the right side is a little bit smaller. So I will just show you the video here. When we put the dye in the main flow, let's go direct to the outlet. But if we have the dye in, let's say, the left side, this is bigger and it moves backward, opposite the direction, and then translating with the main flow. And this is the eddies. This is the circles we have it and the warp transition. The left side is a little bit smaller with less intense eddies. And at the end, we can see that the circles here, this is the flow separation. This is cause the turbulence and the reduced efficiency of the warp transition. Now, the turbulent kinetic energy, we always use it because this is referred to the shear. If we go from bottom to the top, we can see these hot spots here in the middle. This is circles. This is, we always concern about turbulence because this is indicate the ability of water to transport sediment. So this is big problem in the open channels. As we can see, if we go upward to the upper level, we can see that we have a new spot here and it's bigger in the water surface. It's expanded or make stronger turbulence from the bottom to the top. Now the shear stress secondary, this is referred to the flow going opposite sides. So this is the flow here, the cores in the bottom left side is the eddies. So this is the main flow. And when we go further to the downstream, we can see that this turbulence is intensive, but it's a little bit smaller. It means is asymmetric, is not uniform. So this is make the bigger problem and the erosion risk in the downstream earth channels. Now the conclusions, we see that the jet-like cores, and we also we have asymmetric flows, complicated shapes, and we can see that we need the warp transition itself. It cannot stop these turbulence or eddies. So we need to have tools. We have like measurements, appurtenances that can remove or reduce this turbulence in the warp transition. So this is the open channel, and in my research, I propose a new device that is efficiently reduced by install honeycombs in the inlet of the warp transition that control all these turbulence and the problem, because we cannot use the warp transition. Some researcher use veins that they divide the flow, and some they use humps, raise the bottom of the channel, but all these make more turbulence, and because the surface contact area is large, but this honeycombs was efficient to reduce the water turbulence. Thank you very much. Any question?